This is a brief introductory lecture, not even a lecture really, just an introduction overview to the material in Chapter 2, which is the first mechanical material that we'll be looking at for the course. And so I just wanted to walk you through some of that to help give you a sense of what are we trying to accomplish through this chapter and through this section of the course material. So we've spent a lot of time, certainly last fall and even to this point in the class, additional time working with electrical systems where the elements of choice, or the building blocks of our linear system, are comprised of resistors, capacitors, and inductors. And it turns out that the same parallel or an analogous situation exists for mechanical systems. And so, and just like in the electrical systems, we write equations of conservation, okay, like KVL, which is conservation of energy, or KCL, which is conservation of charge. Here we're going to write a conservation equation as well, which is basically free body, summing forces acting on free bodies and summing those forces to zero. So that's like a KVL, because a voltage is like an effort, and when you apply a force or a torque on an object, we can think of that as being an effort. Okay, so very analogous, but because of the context, being one more electrical, one more mechanical, the people who developed the material kind of have different ways of thinking about it, and so it looks different, but in the end, I just want you to kind of step back and realize these are the same, it's the same math underneath all of it, okay? So the way this chapter starts out is that you're going to learn about inertial, compliant, or stiffness, and damping elements, all right, as well as forcing elements. Okay, so that's like your voltage or current source. And everything is lumped parameters, okay? So if we have a mass, we treat it as a point mass. Just like when we have resistors, we treat them as a point resistance rather than a resistance spread along some wire, etc. And then we're going to apply Newton's second law of motion to formulate the mathematical models of these basic systems. And in this chapter, they're all focused on single degree of freedom systems, but they're dynamic, meaning they change in time. So you should feel at home here, or depending on your perspective, at least you'll recognize where we are, because this is what we've been doing, is looking at things that are dynamic even if they were electrical. So here we are doing the same thing for mechanical systems. And then there are sections in the chapter where there's a focus on analyzing the natural response, okay, or where there's no external force acting. There's no loss, maybe. The first ones they look at, it's just like a spring and a mass, and the thing just oscillates forever, and you're trying to determine what is the frequency of oscillation, and what does it look like in time given some initial conditions. And then the free damped, which is just like an RLC, you've added some damping, and now so you have decayed sinusoidal if it's underdamped, or you have two real poles and an exponential decay, combination of two different exponential decays if it's overdamped. And then forced vibrations, okay, forced. So this is nothing more than steady state sinusoidal response, okay. And the thing to keep in mind, the way they do it in this chapter, they have not introduced Laplace transforms, so they're doing everything in the time domain. So as you read through chapter 2, starting with section 2.1, and then 2.2, you'll see that everything is done time domain wise. However, and so the first 2 days in class where you spend time working through some examples from the book, I guess actually the second day is where you actually will start solving some dynamic systems, and you'll be writing some equations of motion using Newton's second law. That'll all be done in the time domain, so it'll be differential equations. Right. When you get to, I think, the third day that we spend on mechanical systems, I point you to some hand notes that I've made, and there I want to leverage off of the concept of impedance, mechanical impedance, and really the concept of or the tool of Laplace transform. And so there we can write the equations of motion, really Newton's second law of motion, without ever writing a time domain differential equation. Okay, and you won't. I just want to let you know you won't see that here in chapter 2 because they don't introduce Laplace transform until chapter 6, I think, or 5. On the other hand, I'll tell you that some of the material in this book is advanced, and we're not going to be digging down in all of it. It assumes some background in mechanical systems that you won't have, that I won't have, to be honest. And so actually moving over to solving the system with the Laplace transform and using impedance concepts can actually end up being a simpler method than some of the things that some of the approaches they might use. Okay, so the goal in adding this other approach from what the textbook has actually the goal of making things more accessible to us, not less. Okay. All right. So the other things that they introduce here is you'll see some use of MATLAB, and I'm going to have you do that in class at least one of the days for the last 20 minutes or so. I want you to go to the stations and actually follow some of their prompts to solve their example problems in MATLAB. And then they do introduce Simulink at the end. You'll be introduced to Simulink in lab. It'll be after spring break. But yeah, we won't be talking about that in the coming 2 weeks. Okay, so I'm not going to go through all of this, obviously, but just a quick tour here. 2.1 is introducing the basic elements of inertia, stiffness, damping, and forcing. And that's your first reading assignment for, I have to check, I think it's for Friday. So reading about inertial elements and then secondly spring elements. Okay, and then later they talk about damping elements. Okay, viscous damping, and the idea there is you've got some mass that's flowing through fluid, and there's a stationary fixed surface and there is a moving surface, and between those two surfaces there is a fluid, and so there's the shear stress on the fluid, and there's a velocity gradient on the fluid that's against the wall that's stationary, has no velocity, has zero velocity relative to the stationary surface, and the fluid that's up against the mass that's moving has a velocity that's essentially equal to the velocity of that moving mass. And so everything in between there, that fluid has a varying velocity, and there's shear forces there based on the viscosity of the fluid, and that results in a drag that this mass experiences. So anyway, they go through at a high level, and in the end you just want a coefficient like resistance. In their case they call it C for a viscous term. The other thing I should point out, and I apologize for this, the notes that I wrote were written before I had this textbook, and so I used some different conventions. So I think you'll see that instead of using C, I use like B or D in the notes. So just keep that in mind. Know that there's not a one-to-one between the text and the notes. So after the section 2.1 that introduces the elements, section 2.2 then is where you start using those elements to solve dynamic systems. And before they can do that, they introduce, what is the tool that we're going to use? What's the physics that we're going to use to solve this? And it's essentially Newton's second law. So the acceleration of a mass m is going to be equal to the net force that is acting on that mass. Okay, so there might be an external force. You're pushing on this mass. There may be a drag force that is resisting motion. That would be part of those forces. There could be a spring that's attached to the mass that's pulling back on it as it moves in a positive x direction, and that would have a force. And so in the end, this is essentially KVL. Okay, you may not think of it as KVL because we would normally just write for KVL, we'd say the sum of all the voltages is equal to 0. And in fact, there is a relationship or a principle in mechanics that is, let's see, here they actually mention it here. It is right here, D'Alembert's principle. Okay, and I'd recommend that you look it up, because I think the way that I typically solve or think of solving these problems, and what will be reflected in the notes, is that I'm actually using D'Alembert's principle. And his principle basically, although there's some subtle fundamental differences, in the end it's the same physics. Okay, the way that he solves these mechanical problems is, instead of saying the acceleration, the inertial force of this mass is equal to the sum of the forces acting on the mass, what he says is we're going to treat the inertial force as actually a force that is acting on the mass. Okay, and people will say that is an imaginary force. Okay, it's an imaginary force. If I was watching, let's see, if I was standing on the ground and there was a ball that was suspended by a cord, and someone applied a tension on that cord and accelerated that ball upward, okay, as an observer, I would note that that ball is accelerating upwards, okay, and I wouldn't feel anything, but I would see that ball accelerate. All right, and we might say that the acceleration of that ball, x double dot, is equal to 1 over m times the net forces acting on that ball. And the net forces in that case would be the tension of the string pulling up on the ball minus the force of gravity, right? Now, the way that D'Alembert solves it, and the way that I tend to think of it in my notes, is if you were to now say you didn't weigh anything and you stood on that ball, okay, and now the same thing happens. Someone pulls on that string and accelerates the ball. All right, you would actually in that case feel an acceleration, right? And that acceleration, there'd be an inertial force that you'd feel, which would be the mx double dot, right? And that's how D'Alembert actually describes or solves these mechanical systems. So what he'll say is the sum of all of the forces acting on a body, including the inertial forces, mx double dot, are equal to 0. Okay, which you might say, well, duh, that's exactly what equation 234 is here. And it is. But I went online and read some forums and some discussion because I was a little unclear on it, and it gets kind of technical, and I think that, you know, one would appreciate the distinction more the longer that one would spend, you know, thinking of this. But from an engineering perspective, in the end, it's the same thing. You're going to sum all the forces, and they're going to add to 0, and they'll add to 0 if you include the inertial forces. This is very analogous to when you know what D'Alembert is trying to do is to extend the principle used when solving static problems, and that is just summing all of the forces on a mass. They all sum to 0, and of course that's in a case where there is no acceleration, right? And what he says is you can actually model a system that does have acceleration if you include the inertial force mx double dot in your sum of forces. Okay, if that didn't make sense, don't worry. I think it'll kind of become clear as you go along and you work some of these problems. So in this chapter, both translational and rotational systems are used. So here's the Newton's second law for translational. Here's Newton's second law for rotational. All right, they use J for rotational inertia or moment of inertia, and theta is the angular displacement. Okay, and here there's sections now on the free response, on let's see, there's free response, there's dampened response, and I might have missed that. And then they actually talk about some forced response as well. Okay, let me pause here and jump over to my hand notes. Okay. And, oops. So for the hand notes here, what I have are translational mechanical systems and rotational systems. There's more after that. You don't have to worry about any of that right now. And I will So at some point I would like you, this is prior to, I have it on the schedule, I don't recall offhand, it's the third day, so I think it's like the Thursday of week 8. You're going to work some problems or some exercise that are found in these notes, and they're rotational problems. So, and I ask that before class you actually will look through these notes so that you can be better ready. A lot of this that's developed early on are things that if you're reading chapter 2, section 1, for instance, you will already know about the basic elements. You'll know about how to put springs in parallel or in series and that sort of thing. Now, what I start off right from the beginning here, which the book does not do, is to, for the spring, for the viscous damper, and for the mass, I have not only the integral or differential form and the time, but I also have an impedance term, okay, an impedance definition. So mechanical impedance, the one we're going to use actually that you'll see me using, is this one that's what's called here velocity impedance. So the analog is very close to electrical, right? So for electrical impedance we have voltage over current. And so the voltage is an effort and the current is a flow, right? Coulombs per second. So it's very natural then to talk about a mechanical impedance that would be an effort like force divided by a flow, which would be, virtual, not literal flow, but it's meters per second. Okay, so newtons over meters per second, those are going to be the units for mechanical impedance. And so you can see that, for instance, for a viscous damper, which is analogous to a resistance, the impedance of a viscous element is just B. I told you I use B. The book uses C, but it's the viscous coefficient. It's analogous completely to the resistance R of a resistor. Okay, and here for the inductor, you would see S times M instead of S times L for a. Did I say inductor? I meant mass. S times M rather than S times L for an inductance. All right, and then lastly, the one that's a little bit different is for the spring, we actually have K over S. So for a capacitor, which is analogous to a spring, you'd be used to 1 over SC, right? And this is in fact what the spring is. You can actually define a spring's compliance, right? The spring's stiffness is K, and by definition the spring's compliance, I'm not sure if they actually talk about it in the book or not, but you can look this up. The spring's compliance is defined as 1 over the stiffness. So if you were to write the impedance of the spring in terms of its compliance, it would be precisely 1 over SC, where the C would now be the compliance, maybe we say C of K or something, compliance of the spring. Okay, so I just want to give you a little preview that in the end, though the textbook is going to be writing Newton's second law all in time domain with x dots and x double dots and theta dots and double dots and so forth, that as soon as you want to, you can come over into the impedance domain, in the Laplace domain, and be solving these problems in the S domain. And to do that, you're going to use these kind of impedance terms here. And the examples that you'll work on the Thursday, I think, no, Wednesday of week 8 will actually have you do that. So I'm going to scroll down. I work a lot of examples, and the examples you're going to be working, let me just get, maybe you should just, well, you can look at this on your own, but you can see the types of problems that we might solve here. So you've got a train, or a truck and a trailer, and there's some compliance, a spring, a stiffness in the coupling. There's some friction between the road and each of the vehicles, and there's a force that is being applied up here from the truck. That would be the force due to the engine, right? And of course it would be applied down at the wheels through the attractive force, but we model it this way. Basically you're pulling on the mass. And things that you might want to know are, what is the displacement x as a function of the force that you put in here. So you might write a transfer function like this one, or maybe you want to know what is x1 as a function of the force, and here you have this this transfer function. So, of course, once you have the transfer function, we can solve all sorts of things with the Laplace transform, right? We could say, what is the step response? What's the impulse response? How does it respond to a ramp, or whatever the case may be? Okay, so those are types of systems that you might encounter for translational. Here's a sample of a very simple model for a vehicle suspension. Okay, so take a look at those. Although the exercise you'll be doing in class will be under this section here, rotational systems. So there's a handout that will have these exercises, begin with exercise 6.2, and you'll get a chance to work on those together in class. Here's a table that is similar to the one that I had before for the translational. This one is for the rotational elements, and you can see the impedance here. Again, it's going to be effort, or torque, divided by flow, which in this case is radians per second, angular frequency. Okay, and things that we'll model are things like this. Here you have a rod, okay, that is held, supported at two ends by a bearing, and that rod has some mass, has some rotational inertia to it specifically, and there's some friction between the bearings and the rod, and we're going to apply a torque at this front end. The external torque here I call capital T of S, and there's going to be a displacement theta 1 at this end, and then we're going to say theta 2 at the second end, because in theory, or in principle, if there is some compliance to this rod, this axle, it could actually twist under differential torque, right? If you held the one end and you applied a torque at the other end, you could actually twist such that theta 1 could be different than theta 2, theta 2 being 0 in this case, and theta 1 being something non-zero. So being a lumped element system, the way that we model this sort of system is that we're not going to do the real analysis on this, right? Everything's distributed. The spring, the inertial, or the moment of inertia, it's all distributed throughout this. We're going to do a very simple model. What we'll do is we'll chop it in two, and we'll place half of the rotational inertia for half the rod on the front end here. We'll put the other half over here, and then we will come up with a lumped spring constant. And actually, in this class, we're not going to spend time trying to derive what the spring constant is. I mean, that's a different course. What we're interested in is just trying to model systems that have been parameterized and lumped in this manner. So can we write the equations of motion based on this lumped element description, and then can we do predictive work on how the system is going to respond to different inputs? Okay, so know that in the end, the book sometimes spends time actually deriving some of these things, like let's derive what is the spring constant, and that's all good and well, but that's out of scope for what we're doing here. Okay, and the basic idea when you're going to solve this kind of problem, it is Newton's second law. Okay, but again, the way that I tend to look at it is more in keeping with D'Alembert's principle, I think. And so what the approach is, you sum all of the torques first for each free body. Okay, so in this case we have, what you want to do is you look at this system and you say, how many degrees of freedom are there here? Like, how many things can twist? And you see that there are two. There's theta 1 and there's theta 2. If I hold theta 1 fixed, I can twist theta 2, or vice versa. Okay, so they both can turn. So for each free body, okay, in this case J1 and J2, we can write a torque equation. All right, so what we'll do is we're going to sum all the torques that oppose positive motion of J1. All right, and we're going to say those are going to be equal to the sum of the torques that enhance positive motion of J1. Okay, and then we can further break this down to there's the sum of torques due to J1, all right, and that's going to be equal to the sum of torques due to free bodies that are connected to J1 via some kind of impedance. So in this case here, what we have is the fact that there is a spring connecting these two elements means that the motion over here at theta 2 will actually, through the spring, apply a torque on J1 and affect its motion. Okay, And then secondly, we'll sum all the torques that are external on J1. And here, the external torques are going to be just this applied torque. The assumption is at this end of the rod, we're going to be applying, maybe there's a motor or something that applies a torque. All right. So that's the approach, and you'll notice that I use ideas of impedance here very quickly. So what I would do is, before, this is just a FYI, before you get to that class, let's just pull that up and see which day that is. That is going to be on 8/3. No. Yes, on 8/3. So this is the Wednesday of week 8. You're going to actually be working through some rotational system exercise handout problems in a handout, and they're actually going to be these problems starting with 6.2 right here. There's a couple problems. So what you really want to do before that class is you want to study these. All right, and if you have questions, then bring those questions. And yeah, if you have questions that Mr. Bosson had, that you can pass to him. If he's not able to help you, he can also try to contact me. I have no idea whether I will have access or be able to really stay up on things, but I will do what I can. Okay, so I think I will stop here. This went longer than I expected, but so this actually is probably going to be enough to cover, probably all I'm going to be able to say at this point for all of the mechanical content that you're going to be looking at here over the next 2 weeks. And in the end, if you find it really difficult to, what I'm asking you to do, first off, what I'm asking you is just to be diligent in reading the assigned reading. It's not long. I didn't ask for a lot to be read, but do the due diligence to study that as best you can, and use the time well in class. And if it turns out that you're struggling with the material and people just aren't getting it, well, that's what we have. We'll deal with that after spring break, and because we'll be continuing on with this material for some time, for a bit after coming back for spring break. So I just wanted to make sure that I had exercise and things for you to do, and I hope that you find the time profitable, even though there's not going to be regular lectures as you would expect normally. So I will end that at this point, and I wish you all well.